right.
All right, let's stand up. Let's stand up. You need to stand up. Let me see as many faces as I can. Where is everybody? Hopefully people are going to get on here in just a second. Let me see as many faces as I can. I can see as many faces as I can. Okay, how many people got my email? How many people got my email over the weekend? Did anybody get my email? Okay. Okay, good. Let's sit back down. I was just thinking about teaching integration in polar coordinates, and I know just how hard it is for you guys to see the board with Zoom. So I decided to do a flipped, I guess I shouldn't put air quotes, okay, do a flipped classroom. How many people have had flipped classrooms before? How many people have had flipped classrooms before? So you know the technique and you hate it, okay? You know the technique and you hate it. Okay, so what I did is I created three videos, 3 half-hour videos talking about integration in polar coordinates. The first half hour is pre-calc. It's just an introduction again to polar coordinates, because a lot of you guys haven't seen that probably since high school. And it's not a great introduction. It's just the bare bones basics of what you would need to be able to do the homework in 15.3. Then I derived polar integration. The hardest thing for kids to understand in polar integration is that when we're doing integrals in terms of x and y, Cartesian, the differentials are dy dx or dx dy. But in polar coordinates, it ends up being r dr d theta. Say what I just said.
R dr
d theta.
And this R confuses the heck out of kids. Where does the R come from? So ask that.
Where does the R come from?
Okay, that's in video 2. Where the R comes from is in video 2. In video 3, we talk about actually doing integrals. So what we're going to do on Wednesday is I'm going to work kind of homework questions with you. So we're going to kind of do your homework together on Wednesday. Is this okay? So you guys have to watch the video between yesterday and Wednesday, taking notes, teaching yourself, and then we're going to do your homework together on Wednesday. And then you have your final quest when? When is your final quest?
Monday.
Monday. What time? 8 horrible a.m. 8 horrible a.m. It will be over Zoom. I'll send out instructions later in the week. Okay, you have to have video feed. You have to have video feed. The department's really trying to clamp down on online. We'll just call it discrepancies. We won't use a more nasty word. Okay, they're really trying to clamp down. Okay, and we've been ordered to do whatever we can to try to stop that. So you're going to be on Zoom. I'm going to record you on Zoom, but I'll send out that information later in the week. It's not going to be a final exam, which kills me. I always love final exams, cumulative final exams. What do my students actually know leaving my classroom? This year it's just a final quest. The syllabus isn't right anymore because we're not even doing a project. I threw that out the moment we went online. So you're going to have your 6 quests and your web assign, and that's what your grade's going to be based on. You'll add up your 6 quests and divide by what? You'll add up your 6 quests and divide by what? They're worth 50 points each. You guys tell me, you're in Calc 3. You'll add up your 6 tests and divide by what? 300, which is all the points possible for the quests. Okay, that's worth 85% of your grade. And then the other 15% is from your web assign. So I'm going to assign another web assign for this Friday. That's going to come directly from the homework. That's going to come directly from the homework in 15.1, 15.2, 15.3, and 15.6 to help you get ready for your quest on Monday. To help you get ready. Are we all on the same page? Okay, stand up. I think the integration chapter is one of the easiest chapters in Calc 3. So it's nice that we saved it towards the end. Okay, so let's sit back down. The hardest thing, guys, the integrals are not bad. You did much, much harder integrals. You did much harder integrals in Calc 2. And as far as compared to like infinite series, are you kidding me? How disturbing was that? To converge or not to converge? That is the question. Power series, Taylor series with remainder. I know you're having shakes just thinking about this stuff. This stuff is not that bad. If you know how to integrate x to the fifth, how do you integrate x to the fifth? You should know how to integrate x to the fifth. How do you integrate x to the fifth? What's the integral of x to the fifth? X to the sixth over 6, and then you got your plus c. How do you integrate e to the x? What's the integral of e to the x?
E to the x plus
What's the integral of cosine? Sine. And the other thing you might need is integration by parts. You remember integration by parts? Yeah, you didn't enjoy that, did you? The integral of u dv is equal to uv minus the integral of v du. But these are basic integrals. The hardest thing is that in the limits of integration, now you have functions of x or functions of y. Okay, so I'm going to talk about my type 1 integrals and my type 2 integrals. And this is not going to be exciting. You're going to have to focus to stay awake. So tell yourself to stay awake. Okay, put your hands on the space bar. Tell each other to stay awake.
Stay awake.
Okay, I'm not real confident at all. Cameron, I don't think you said anything. Are you there, Cameron?
Yeah.
Okay. Nick, are you there? Nick.
Yes, sir, I'm right here.
Okay. Robert, are you there?
Yes, I am.
Roberto, are you there?
Yeah.
Okay. We have, can you read that? I'm now out of the picture. What does that say?
Type 1.
Type 1. If there's a type 1, there's going to be a type
2.
or we wouldn't use 1. Okay, type 1, my type 1 domain, if I'm integrating over a space sheet to get assigned volume, I'm integrating over like some function xy. Z equals f of xy. When I say z equals f of xy, you say space sheet. So we're integrating over a space sheet down to a domain. And the two major types you're going to have to integrate on Wednesday are type 1 domains and type 2 domains. Do they look exactly the same? And the answer is no. If I look at type 1, I've got functions of x. Does this pass the vertical line test? Do g and h pass the vertical line test?
Yeah.
But over here, would these pass the vertical line test? So in my type 2, these are not functions of x. But turn your head this way. They are functions of what? Why? If I think about a vertical line test being like this, for every value in the domain between c and d for y, my function g of y and h of y only hits one value over here in my range axis, x. Okay. Now you guys help me out. In my type 1 integral, x is running between A and B, and for every x, so mark an x on in between A and B, mark an x in between A and B. Y is running between, the corresponding y is running between the functions,
G of x and h of x.
G of x and h of x. And then what we talked about, really exploiting a lot Fubini's theorem, was that we could trade the double integral over the space sheet to be two single one-dimensional integrals integrals that take the following form. As x goes between a and b, as x goes between a and b, y runs between
G of x and h of x.
g of x and h of x. And then we've got our space sheet. My inner integrals with respect to y, and my outer integrals with respect to x. So you first do your integral with respect to y, thinking x is a constant, and then you finish the problem. Doing your integral with respect to x. Now for type 2, it's just the opposite. For every y between c and d, the corresponding x runs between
C and
between g of y and h of y. As y goes between c and d, the corresponding x goes between g of y and h of y. So write down the double integral. That would represent that volume, that if we're integrating f of xy over d. Okay, and what do you guys have? What do you have? The integral from, I'll keep going. I'll start rapping. You don't want to hear that. The integral from C to D. Say that, rap with me. The integral from
D to D.
C to D. Let's try it again. Let's get our rap right. The integral from C to D. And as y goes between C and D, x goes between, it's not going to rhyme.
H of y.
Yeah, G of y and H of y. So yeah, it's like a 60-year-old white rapper. Okay, that's what I am. Okay, so now we're here doing calc rap. Okay, as y goes between C and D, x goes between
G of y and h of y.
G of y and h of y. And then we're integrating over our space sheet. We're first doing our integral with respect to x, and then our outer integral is going to be with respect to y. So the beauty of Fubini's theorem, say that. The beauty of Fubini's theorem is that we can use two one-dimensional integrals to do a two-dimensional integral. We can use an iterate means to like do one thing after another. We can do an iterated single integrals using the fundamental theorem of calculus from Calc 1 twice, instead of coming up with a multi-dimensional version of the fundamental theorem of calculus. How many people are happy that we're not coming up with a two-dimensional fundamental theorem of calculus? How many people are pretty happy with that? Or a three-dimensional at this point in the semester? How many people are pretty happy that we can just use our one-dimensional to do these problems? Okay, so that's the beauty of Fubini's theorem. Now what I've got here is two double integrals. This is a type, and I've kind of made it easy for you. This is a type 1, and this is a type 2. And so we can see, as y goes between C and D, x goes between 0 and y squared. But over here, we've got as x goes between 0 and pi over 2, y goes between
0 and x.
0 and x. So guys, I'm going to make a deal with you. I'll do that one, and you'll do this one. You agree or disagree? There is no deal. This is my class. Okay, I'm the Ayatollah. I told you. Okay, I will do this integral as an example, and you're going to do this integral. Okay. Go to grid view, go to grid view, go to grid view, go to grid view, go to grid view. Go to grid view. Look at those faces. Do those faces look beaten? Do those faces look worn out? Look at those faces. Look at Zach's face. Zach, how are you doing, man? You with me? Okay. Look at Red's face. Look at Red's face there. Stuart got through COVID and everything this semester. Yeah, sorry, I shouldn't have said that. Okay, all right, okay, here we go. Let's make me number one again. Make me number one again. Okay, I want to do this type 2 integral. So I'm going to start with the inside integral. And I'm going to try to use the fundamental theorem of calculus. Now I notice that I'm integrating with respect to what? Can you read it? Can you read it? Let me read the integral. The integral from 0 to 2, because I know we're zooming. The integral from 0 to 2. Y is going between 0 and 2. X is going between 0 and y squared. And my space sheet f of xy is x squared times y. Okay, and then I'm integrating with respect to x and then with respect to y. In that inner integral, who can behave like a constant, the x squared or the y? In that inner integral, who can behave like a constant, the x squared or the y? The y, because I'm integrating with respect to x. So let's pull that y out to there. Let's pull that y out to there. And so this would be the same thing as the integral from 0 to 2 of y times the integral of 0 to y squared of x squared dx dy. How many people are with me so far? How many people are still in the game? How many are still on the field? Okay, now let's use the fundamental theorem of calculus. Is the integral of x squared that hard? Can anybody think of a function whose derivative is x squared? Yeah, I realized in my first section I put on the wrong shirt today. I didn't grab a JMU shirt, and then I looked at what I had written on, and I had my. Let's pretend that isn't there, okay? Just pretend pretend like that's blocked out like they do on TV. Okay. So using the fundamental theorem of calculus the first time, this is like x cubed over 3. Here's a function whose derivative with respect to x is x squared. I put a line. I put my 0 and y squared. So this integral is equal to this integral, which is equal to this integral, which is equal to this. What does the line mean from Calc 1? What does that line mean from Calc 1?
How do we do that?
So I would stick the y squared in for x. Wherever I see the x, I stick the y squared. And wherever I see the x, I put a 0. And we're now saying, thank you, Stuart, for writing a problem where I'm putting 0 in. So then I would get the integral from 0 to 2. This y is the same as that y. That y is the same as that y. It's just hanging. Then I get y squared cubed, which is y to the 6th over 3 dy. How many people are still with me? How many people are still in the game? Okay. The 3, I'm just bringing it out front as a constant. But y to the 6th times y is y to the 7th. Now we're really just back to Calc 1. Now we're just really back to Calc 1. Whose function's derivative with respect to y is y to the 7th? Whose function's derivative with respect to y is y to the 7th? Anyone?
1/8 y to
1/8 y to the 8th. So I'd have 1/3 y to the 8th over 8, and then I would have this evaluated between 0 and 6. Okay guys, what will you not be allowed to use next Wednesday? What will you not be allowed to use next Wednesday? A calculator or technology of any kind. No calculator. So here's the deal. I believe everybody knows this line means you plug the 6 in for y and you plug the 0 in for y and you subtract. Are we all going to agree that everybody understands that, or they wouldn't be in Calc 3? Do we all agree with that? Okay, so at this point of the problem, you could put a box around it and abandon it. At that point of the problem, you're done next Wednesday. I don't need to see you do the arithmetic. I don't need to see you try to figure out what 6 to the 8th is, and then deal with the 0. So you're done at that point. Calc 3's over. Do we agree or disagree? Do we agree or disagree? Okay, so now I made a deal with you. I was going to do the type 2 integral, and you were going to do this type 1 integral. So let me read it for all of you blind Zoomers. Okay, it's the integral, x is running from 0 to pi over 2. It's the integral from 0 to pi over 2. Y is running between a function g of x equals 0 and a function h of x equals x. The space sheet is x times the sine of y, and your first integral is with respect to y, and your second one-dimensional integral is with respect to x. You have at it. You have at it. Okay, now you're going to talk about what you're doing with each other. I'm breaking you into breakout rooms. So that was a total failure, wasn't it? That was a total failure. I brought you into breakout groups and nobody talked, did they? Nobody talked at all. Did anybody talk? Did anybody talk? Raise your hands if you actually said a word in a breakout group. Raise your hand if you actually said, Cosmo, you didn't say one word, not one. Stuart, where's your hand? Was your hand up? Was your hand up? Okay, breakout groups. Okay, all right. I saw the thumbs up there. All right, here we are. How many people got to here? How many people got to there where they pulled the X out? How many people got to there? You were here. How many people pulled the X out? I want to see your hands. I want to see your hands. Okay, if you look at this integral, guys, you're integrating with respect to y. Partial integration. X is a constant, so you can pull that out. Now, how many people knew the antiderivative of sine? What's the antiderivative of sine? Whose function derivative is sine? Negative cosine. So I've got the negative cosine of y. I'm evaluating between 0 and x. The line means plug in and subtract. So I'll plug in the x, and I get minus cosine of x, then minus cosine of 0. But cosine of 0 is what number? It is on the board. Cosine of 0 is what number?
1.
1. So now I've got the integral of x times minus cosine of x plus 1. Did anybody make it that far? Did anybody get to that point? Okay, good. A couple of people. That's good. Now, let's distribute the x. I'll get a minus cosine of x plus x. I'll get a minus x times the cosine of x plus x. And then I'm going to distribute my integral so that I'm trading this for these two integrals. I'm trading this for these two integrals. My first integral's minus the integral from 0 to pi over 2 of x times the cosine of x. And my second integral is the integral from 0 to pi over 2 of x. Which integral would you want to do, and which one would you want me to do? Which integral would you want to do, and which integral would you want me to do? Do you want to do the first one or the second one?
Second one.
The second one. Whose function's derivative with respect to x is x?
1/2 x squared.
1/2 x squared. Thank you, Michael. Thank you, Michael. So if you're looking here, we've got then this is equal to minus the integral of x cosine of x, 0 and pi over 2. And then I've got the second integral that we've just done. Michael's done it for us. X squared over 2, evaluated between 0 and pi over 2. Now on Wednesday, you're done with which part? On Wednesday, you're done with which part? On Wednesday, you're done with your second integral. I don't need to see you plug in the pi over 2, and I don't need to see you plug in the 0. Let's talk about doing this integral. Math 236, what integration technique are you going to want to be able to do the integral of x cosine of x?
Integration by parts.
Thank you. Integration by parts. Very good. Very good. So remember, here's your integration by parts formula. You're like, Dr. Warner, I don't remember it at all. The integral from a to b of u dv is equal to uv times minus the integral from a to b of v du. So you read what I just wrote, you read what I just said. You read what's on the board. You read. What is it? What do you have here? What do you have?
Integral from a to b of u
Equals UV UV from A to B minus
minus the
the
integral
integral from A to B of V du.
Okay, so guys, whenever you're doing integration by parts, you can always do integration by parts. You can almost always do integration by parts on almost any integral. The problem is, it's usually a disaster. Only certain kind of integrals work well with integration by parts. Typically, when you make this trade for this trade, it's a bad trade. It's not a trade you want to make. It's like trading Tom Brady. It's like trading Tom Brady for Peyton Manning. That's not a trade you want to make. That's not a trade you want to make. Okay, you want to keep Tom Brady. Or you might want to trade Tom Brady for, who did they trade for? Who did the Patriots get? Who did the Patriots get in that trade? Does anybody remember?
Cam Newton.
Cam Newton. That wasn't the best trade. That wasn't the best trade. Okay, in this case, the trade's going to work well. Here's the integral I'm trying to do. Forget the minus right now. I'm trying to do the integral from 0 to pi over 2 of x cosine of x dx. Now I have to choose u to be something, and I've got to choose dv to be something else. I've got to be able to integrate to get v. Well, you can integrate x and you can integrate cosine. But if you integrate x, you're going to get x squared over 2, which is just going to make the integral worse. So you're going to want to let u be equal to x, and you're going to let dv be equal to cosine of x. How many people remember doing integration by parts? How many people took Calc 2? How many people took Calc 2? Then you did integration by parts. Then du is equal to the derivative of x, 1, times dx. V is equal to the integral of cosine. Whose function's derivative is cosine? Whose function's derivative is cosine?
Sine.
Sine, so v is equal to sine. Now let's use our integration by parts formula. Let's use our integration by parts formula. This integral would be the same thing as u times v, so you tell me what that would be. I'd write it down and you guys wouldn't see it and then you wouldn't learn anything. U times v. What is that? What is that? What is that? U times v.
X times sine x.
X times sine x. Line 0 and pi over 2. Minus the integral of 0 to pi over 2 of v du. Now what is v du? What is v du? What is v du?
Sine x.
Sine
Yes.
So at this point, guys, you got to always ask the question: good trade or bad trade? Good trade or bad trade? Did we trade? We traded integrals. Good trade or bad trade? Did we end up with something that's easier or harder? Did we end up with something that's easier or harder? Easier. Whose function's derivative? Whose function's derivative is sine? Whose function's derivative is sine?
Negative cosine.
Negative cosine. So this would be x sine of x evaluated between 0 and pi over 2, then plus cosine of x evaluated between 0 and pi over 2. Now, can you just leave it in that line form? Can you just leave it in that line form? Can you just leave it in that line form? Yeah, on Wednesday you can just leave it in that line form. How many people are beginning to understand at least a little bit, remembering some of the integrations and things like that? I recognize this is not that exciting. The integrals aren't that challenging. So it's not that exciting once you actually learn, oh, I'm just plugging functions in. It's not that exciting. So let's make it more interesting. Let's stand up. Let's stand up by making it more interesting. What can I do to get my students awake? Okay. Let's sing the fight song. Let's sing, no, Dr. Warren. Put your hand on the space bar. We're singing the fight song. We're gonna be dukes. I went here, you went here. Let's put your hands on the space bar. Put your hands on Madison, James Madison. We are the Dukes of JMU. Madison, James Madison. I don't know the rest of my song.
I'm
The fighting
So
begins.
JMU,
Fight for glory.
glory.
Honors won. Brighten the lights, Madison.
Thank you, Caitlin. Madison, I know this part. James Madison.
Show your colors, proud and true. We are the Dukes
So
of JMU.
JMU. Yeah. Okay. We've got a lot to learn. I've got a lot to learn. Let's sit back down. Listen. I cannot wait to go into the new basketball arena. I cannot wait to go to the new basketball arena. Okay. I cannot wait for spring football. I can't wait to be in the stadium for spring football. Except I don't think they're going to let me in the stadiums. I think I'm going to be watching virtual Zoom football, virtual Zoom basketball, unless we can get vaccinated. Unless we can get vaccinated. Okay. So who's going to get vaccinated with Dr. Warren? Who's going to get vaccinated with Dr. Warren? Okay, that's nobody. Am I the only one who's going to get vaccinated? Okay, good. Okay. So let's make this a little bit more interesting. Let's pick another problem from the book. These problems were that poor mother. Luke, I'm sorry. Your mother must be wondering what the hell is going on in this class. I'm paying for this. Okay. Let's look at problem number 18. Okay? So in problem number 18, it's asking the following. It's saying evaluate this double integral on the region bounded by the following. So let me write it down. This is problem number 18. So what they want you to do is, over this domain, integrate x squared plus 2y dA. Now, before we even write down what d is, how many people are terrified by the integral? I mean, just looking at the integral, how many people are like, Dr. Warren, that doesn't look so bad? I mean, if you just look at it, it almost looks like high school. I mean, it almost looks like what you would learn in high school calculus. There's nothing interesting with integrating x squared or 2y. What's interesting is in the domain. They want you to integrate over the following. The domain D is bounded by the curves. Y equals x, y equals x squared, and x is greater than or equal to 0. It's bounded, your domain is bounded by the curves y equals x squared, and x is greater than or equal to 0. And what we want to do is find the volume over that D. So now let's go back to high school. Give yourself an xy. Draw y equals x squared, draw y equals x, and try to at least find what D looks like. Okay, hold up your pretty pictures. Let me see what your graph. Let's see what you did. Let's see what you've got. Nice, Luke. Yeah, nice, Cosmo. Excellent, Rhett. Yeah. Raylan, you're going to be on the other side. You're going to be, well, maybe it's just your thing is flipped. Maybe it's just your camera's flipped. You think, good, Michael. Yeah, guys. Okay, good. So you made your high school teachers proud. How many drew something that looked like that? How many drew something that looked like that? Y equals x squared. Now y equals x looks like this. And then we want x being greater than 0. So this is the region. This is the region we want to integrate over. This is the region we want to integrate. How many people are with me so far? How many people were with me so far? Okay, now, looking at this, does it look like we're trying to do a type 1 integral or a type 2 integral? The way they gave it to us, does it look like it's better to set up as a type 1 or type 2? Did they give us functions of x or functions of y? Did they give us functions of x or functions of y?
Functions of x.
Functions of x. So I'm thinking that this would probably be my g of x, and that would be my h of x. Now go back in your notes and look at your type 1 integrals. Go back in your notes and look at your type 1 integrals. You need a g of x. Who's the g of x? Who's the bottom function for that region? Who's playing the role of the g of x? Very good, Stuart. X squared. Who's playing the role of the h of x? Who's playing the role of the h of x, the top function?
Y equals x.
Y equals x. So I know my inner integral is going to be from x squared to x. I know my integral is going to be from x squared to x. I'm integrating the surface x squared plus 2y. My first integral is going to be with respect to y. As x goes between something and something, y is going to be going between my g of x, x squared, and my h of x, x. Now here's maybe the most interesting part of the problem. Who's a and who's b? Here's maybe the most interesting part of the problem. Who's a and who's b? A is not that hard. Who seems to be the a? Who seems to be the a? Just looking at your diagram. Who seems to be the a?
0.
0.
0. Now the better question is, well, who's the b? And this is the trick, guys. It's where the curve x squared intersects the curve x. So just set these equal to each other. X squared equals x. Now I'm going to teach you something. I do not want you dividing by x. I always want you setting these equal to 0. But that's the same thing as saying x squared minus x equals 0. Factor. What can you factor out of both of these? What can you factor out of both of these?
X.
And you're left with x times x minus 1 equals 0. What are your two solutions? What are your two solutions? What are your two solutions?
0 and 1.
0 and 1. If you do it this way, you'll always get your A and your B. Your A and your B. So my A is 0, and my B is 1. Okay, now let's look at the integral. Now let's actually look at the integral. In my first integral, who's behaving like a constant? My first integral, who's behaving like a constant? My first integral, who's behaving like a constant?
The x squared.
The x squared. So if I'm thinking about this, the integral from 0 to 1, then I'm just going to distribute my integral. I would have x squared times the integral from x squared to x of 1 dy plus 2 times the integral from x squared to x of y dy. Now I've got my dx there. So all I've done is distributed my integral, pull out my x squared, pull out my 2. Whose function's derivative with respect to y is 1? whose function's derivative with respect to y is 1?
Y.
Y. So then this would be equal to the integral from 0 to 1 of x squared, y evaluated between x squared and x, y evaluated between x squared and x, whose function's derivative with respect to y is y. Whose function's derivative with respect to y is y.
1/2 y squared.
1/2 y squared. So I would have 1/2 y squared evaluated between x squared and x. And then I've got a dx. How many people are hanging with me so far? How many people are in the problem? How many people are in the problem? Rachel, are you there? Are you with me? Michael, you in the game? You in the game?
Yep.
Nick, how about you? Are you with me here?
I'm right here.
Robert, are you following? Robert, are you following?
Sir.
All right, okay. So now what does the line mean? 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 Evaluate, plug in, and subtract. So looking at this, I'd have the integral from 0 to 1, x squared times x minus x squared. These guys cancel. Plus x squared, plus x squared minus x squared squared, which is x to the 4th dx, which is x to the 4th dx. How many people followed that? How many people followed that move? How many people followed that move? Okay, then we'd be left with the integral from 0 to 1 of x cubed minus x to the 4th plus x squared minus x to the 4th dx, which is equal to the integral from 0 to 1 of x squared plus x cubed minus 2x to the 4th dx. Guys, how many people can do the last integral? How many can take it from there? How many people can take this from here? How many people are like, Dr. Warren, I own that from there on? Hopefully everybody does. Hopefully everybody does. So I don't want to take valuable class time. I don't want to take valuable class time doing the rest of that integral. Okay, look at something that tells time. Look at something that tells time. What time is it? What time is it? What time is it?
7:30.
Okay, what time does class end?
11.
11, not 10:45, not 10:45. It took me all semester, but I finally learned that. Okay, now stand up, because now you're gonna do something that's gonna twist your mind around. This is not going to be fun for you. But it's not that hard. It's not that hard. Okay, sit back down. Unlike in Calc 1 or Calc 2, sometimes you have tricks in Calc 3 that you don't have in Calc 1 or Calc 2. Here's one of the tricks that often proves useful. Some integrals are easier as type 1 integrals, but some integrals are easier as type 2 integrals. And you can often go between the two. Meaning you can change a type 1 integral into a type 2, or you can change a type 2 into a type 1. Okay, so now what I'm going to do is I'm going to show you how you can do that with this integral right here, the one we just looked at. I'm going to blow up my domain. Make it a little bit bigger, easier to see. Now this is like the curve y equals x, but that's the curve y equals x squared. And the way we represented this was, we said that as x went between 0 and 1, say what I just said. Say what I just said, it'll help you.
As x comes between 0 and 1.
0.
As x goes between 0 and 1, y went between x squared and x. Are you following? Are you following? But I can also think about it this way. As y goes between 0 and 1, say that.
As
As y goes between 0 and 1.
X runs between what two functions of y? X runs between what two functions of y? Now this one isn't bad. This one isn't bad. If y is equal to x, then just turn it around. X is equal to y. The other one is different. If y is equal to x, then x would be equal to what? If y is equal to x squared, then x would be equal to what?
Variable.
The square root of y. The square root of y. So we can also do this integral the following way. We can say as y goes between 0 and 1, as y goes between 0 and 1, so my outer integral is going to be with respect to y. X runs between g of y, the lower function y, to the upper function h of y, which is the square root of y. And then we're just integrating our space sheet to x plus y. It just so happened that this integral wasn't any easier this way. So I just had you do it as a type 1 integral. But there's some integrals where it's absolutely crucial. It's absolutely crucial that you change the order of integration. And I'm going to look at an exercise like that right now. No, I think I'm going to do problem number 46, which is a little bit easier. Then we'll do that. So this is problem number 46. What do you have to do between now and Wednesday? What do you have to do between now and Wednesday?
Watch the videos.
Watch the videos and wake up. Watch the videos and wake up between now and Wednesday. Okay, what's next Monday? What's next Monday?
Final.
Quest, yes, our final quest. Guys, it's going to be a 30-minute quest. It's not going to be any different. 30, 40-minute quest, just like the rest of them. It's not going to be a 2-hour final exam. It's going to be a 30, 40-minute quest, just like our other quests. It's going to be over integration and a little bit of theory related to max-min. No max-min problems, just the theory related to max-min. I will put up what flashcards to study. I'll put up what flashcards to study. Okay, here's problem number 46. And I kind of like these kinds of problems. And let me just kind of explain. What we've got here is we've got a type 1 integral. X is running between 0 and 2. Y is running between what functions? You guys, can you read that? Can you read that? Y is running between what functions?
x squared.
X squared.
4. And we've got an arbitrary space sheet. Now the reason I like these kinds of problems is we don't actually have to do the integration. That's not what they're asking us to do. They're not asking us to actually do any real integration. What they want you to do is change from a type 1 integral into a type 2 integral. They want you to change from a type 1 integral into a type 2 integral. So when you've got these kinds of problems, if it's type 1, go look at the type 1 integrals. Go back in your notes and look at the type 1 integrals. This is when I wish I had electroshock. This is when I wish I could, Zoom had an electroshock feature where I could just zap you to wake you up. What are the things that are involved in the type 1 integral? What are some of the letters in there? What are some of the letters? What do you have?
A and B.
A and B. What else do you have?
G of x and h of x.
And what else do you have?
D and C.
Well, no, that's type 2. You got an f of xy. You got an f of xy. And do you have a dx and a dy? Do you have a dx and a dy? You're like, damn it, Dr. Warren, stop. Okay, so now look, this is in type 1. Who's the A? Let's cast our play. Who's playing the role of the A? Can you at least identify that? Who's playing the role of the A?
Yeah.
0. Who's playing the role of the B? Who's playing the role of the B? 2. Who's playing the role of the g of x? Who's playing the role of the g of x?
X squared.
X squared. Who's playing the role of the h of x? 4. The function that's just 4. Try to graph D. Try to graph the domain. Because it's vital when you're trying to switch orders of integration. And shade the area that you think that the D is. Shade the area that you think the D is. Okay, show me your art. Show me your art. What do you got for me? What do you got for me? Show me your art. What do you got? What do you got? Okay, good. Good, Stuart. Nice, Cosmo. Nice, Caitlin. Yeah, great, Rachel. Nice, Emily. Yeah, Rhett, loving it, loving it. Michael, let me see yours. Yeah, good, Michael. Okay, guys. So how many people are comfortable with graphing x squared? How many people are comfortable with graphing x squared? So the book doesn't make it too bad. So there's my g of x. This is like my g of x, my lower function. My upper function is h of x equals 4. It's always 4, goes like that. There's my h of x. My a is 0. My b is 2. Now guys, when x is 2, what's x squared? When x is 2, what's x squared?
4.
4. So you see, we are hitting that point right there. So here's my type 1 representation. Now turn your head sideways. Turn your head sideways. How can I re-represent this as a type 2 integral? Here we're saying as x goes between 0 and 2, y is running between x squared and 4. But now if I'm thinking about this as a type 2, Y is running between what values? Who would be your C and your D if you're thinking about this as a type 2?
0 and 4.
0 and 4. As Y runs between 0 and 4, X is running between what two functions of Y? This would be the function X equals what? This would be the function X equals what? 0. And this would be the function X equals what? If Y is equal to X squared, then X would be equal to what?
Y.
The square root of Y. Again, if Y is equal to X squared, this implies X is equal to the square root of Y. So then I could say that I'm running X between 0 and the square root of Y. And again, I don't really need to do anything because they didn't actually give me an actual function of integration. Guys, is this making sense? Is this making sense as far as... I don't think it's that complicated, but I know when you see it the first time, it seems a lot more complicated. But it's not really that bad. It's not really that bad. Okay, one last problem, and I'm freeing you. One last problem, and I'm freeing you. So here we go. Here's our last problem of the day. It's not that bad. It's not that bad. Once you know how to do double integrals, triple integrals are just the same kind of thinking. So I'm going to read the triple integral to you. Z is running between 1 and 2. We have the integral as z goes between 1 and 2. Of the integral as x goes between 0 and 2z. And as y goes between 0 and the natural log of x. And here's the fun part. Your surface is 4-dimensional. It's a function of x, y, and z. And this is why we don't spend a lot of time on triple integrals, or I don't spend much time in Calc 2 on 3-dimensional functions. Because it makes sense when you say, okay, z equals f of xy, yeah, I can visualize that. I've got a function down here, some domain down here, I've got a space sheet, z equals fxy. I can visualize that. I want some volume under this thing. But here, guys, here, my domain My domain takes up all three of my dimensions. My domain, they don't even use D, is E. In order to plot this surface, you need 4 dimensions. You need a 4th axis. You need like a W equals this. You need a 4-dimensional space. How good are you at graphing in 4 dimensions? You can't graph in 4 dimensions. I can barely even understand 4 dimensions. I know, I've seen people, you can look up hypercube. They try to even visualize what a cube of sugar might look like in 4 dimensions. No, it's real easy to think what a cube looks like. It's real easy to think what a cube looks like in 3 dimensions. But in 4 dimensions, good luck. But we can still do triple integrals, even if we can't visualize what's going on. We can still find our hypervolume. Say that, our hypervolume, more than 3-dimensional volume. Okay, so let's try to do this, and then we're going to end class. And I don't know how much of this I'm actually going to end up doing before I end class. Okay, in my first integral, who can behave like a constant? In my most inner integral, in my integral with respect to y, who can behave like a constant?
X.
X, so let's pull that out. It's just a lot of writing. The integral from 1 to 2, the integral from 0 to 2z, x times the integral from 0 to the natural log of x times e to the minus y dy dx dt. How many people on Wednesday would have at least gotten that far? How many people on Wednesday would have at least gotten that far? Okay, next. I need somebody to come up with a function whose derivative with respect to y is e to the minus y. I need an antiderivative of e to the minus y. Can anybody think of a function whose derivative would be e to the minus y? You could use u substitution, but let's not. How about minus e to the minus y? What's the derivative of minus e to the minus y? What is that? What is that? And so guys, this is probably good to remember for Wednesday. This is probably good to remember for Wednesday. What's the integral of x to the k? 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 I'll keep going.
X to the k plus 1 over k plus 1.
Thank you, Roberto. And then plus c. We're gonna be doing definite integrals, so I'm not gonna put the plus c there. What's the integral of e to the kx for any constant k? What's the integral of e to the kx for any constant k? I don't want you having to do u substitution when you're trying to do this. It's just 1 over k e to the kx. What's the integral of 1 over x? What's the integral of 1 over x? What's the integral of 1 over x? Natural log of x. What's the integral of sine? What's the integral of sine? What's the integral of sine? What's the integral of sine?
Negative cosine x.
What's the integral of cosine? What's the integral of cosine? What's the integral of cosine?
Sine of x.
Sine of x? Okay, the last one you need to remember for Wednesday probably is this one. What's the integral from a to b of u dv equal to? And you better have it in your head. We just did it. What's the integral from a to b of u dv equal to? uv line ab minus the integral from a to b of v du, minus the integral from a to b of v du. Okay, so let's just finish with this. I'm gonna get you to 1 point, and I'm gonna let you go. This would be the same thing as the integral from 1 to 2, the integral from 0 to 2z, x times minus e to the minus y, evaluated at 0 to the natural log of x. And so we're done with our integration with respect to y. Now here's the thing. When you plug the 0 in, what number are you going to get? When you plug a 0 in, what number are you going to get? When you plug the 0 in, what number are you going to get?
You get 1.
You're going to get a 1. And so I'd have a minus, so it's going to end up being a plus 1. Now here, when you plug the natural log of x in, you're going to get minus e to minus the natural log of x. And we still have an x hanging here. We still have the x hanging out front. And then we have the integral from 0 to 2z. We have to do the integral from 0 to 1 dx dz. I'm going to show you one trick and then I'm stopping class. I'm going to show you one trick and then I'm going to stop class. Because the rest of the integral is almost trivial the moment we notice this. Remember that e to the natural log of ice cream cone is equal to e to the natural log of ice cream cone is equal to
Ice cream cone.
ice cream cone. This is not set up to use that. You have minus e to minus the natural log of x. This minus ruins everything. But I can think about this minus. This is not calculus, guys. This is algebra. This is the same thing as e to the negative 1 times the natural log of x. That minus is hanging there, which is the same thing as e to the natural log of x to the negative 1. Now, is this set up so that we can use our algebra flashcard? And so this ends up being minus x to the negative 1. Not a lick of calculus in this. This is all algebra. Which is the same thing as minus 1 over x. Which is the same thing as minus 1 over x. And so this makes our life a lot simpler, because our integral then becomes the integral from 0 to 1, the integral from 0 to 2z, and then I've got the x outside, minus 1 over x inside, plus 1 dx dz. Distribute your x's and you've got super simple integrals to do. Distribute your x's and you've got super simple ones. Okay, I assign homework in section 15.2, 15.2, which is your type 1, type 2. It almost sounds like diabetes. And we got D in there too. This sounds horrible. Okay, we got our type 1, type 2 integrals. Dr. Warren, it feels like diabetes. I feel like I'm going into diabetic shock after today's lecture. And then 15.6, which is triple integrals. Guys, I only assign 3 little integrals for triple integrals. They're not any harder than double integrals. In fact, the problems I assign in 15.2 are much harder than the problems I assigned in 15.6. So I want you working on the homework in 15.2 and 15.6, and then you got to watch the lectures for our flipped classroom, and then we're going to do your homework together. We're going to do your homework together for polar integration on Wednesday, and then class will end. This class will end other than your class. Are we all on the same page? Are we all on the same page? Well, thanks for putting up with me today. I know today this information isn't that exciting, but thanks for putting up with me. Did you guys learn anything? Did you learn anything? Did you learn anything?
No.
Okay. I will pretend like you did. I will see you on Wednesday. I'll see you on Wednesday. Thanks for putting up with Dr. Warren.
Thanks, Dr. Warren.
See you
Thank
guys.
you.
Thanks,
Have a
Dr.
good rest of
Warren.
the day.